Hi Chem 151 students, welcome back for our second lecture on the equilibrium chapter 17. So in the last lecture we introduced the equilibrium constant Kc. In this lecture we're going to introduce a related quantity called the reaction quotient, which has a variable here that is Q sub C to indicate the reaction quotient. We'll also later talk about another K called Kp, the equilibrium constant expressed in terms of pressures instead of concentrations. So let's start with the reaction quotient Q. So like before, we talk about a general reaction here where the reactants, we've called them A and B, and the products we call them C and D, and the little a, little b, little c, and little d represent the coefficients in the balanced equation. So the reaction quotient, you'll see, is calculated as the concentration of the products to their respective powers of their coefficients in the balanced equation, multiplied by one another, then divided by both of the reactants to their respective powers equal to the coefficient in the balanced equation, multiplied by one another on the bottom of the fraction. And so you'll notice this is actually the exact same way that we calculate the equilibrium constant. The difference is that for an equilibrium constant, we would input concentrations for a reaction that is at equilibrium. For a reaction quotient, they can be concentrations at equilibrium or not at equilibrium. They can be any concentrations that exist for the reaction at that moment. And so that's why these are indicated with a sub T here, the T meaning the concentrations at this time, not necessarily the concentrations at equilibrium. So the reaction quotient is defined the same way as the equilibrium constant, except the concentrations in the reaction quotient are not necessarily equilibrium values. In the equilibrium constant, they must be equilibrium values. So what is the purpose of Q? Why would we want to calculate it since it's calculated in the same way as K? The purpose of Q is to actually compare the Q to the K. So the Q tells you basically the state of the reaction at this moment. And then you can, based on the Q, decide whether the reaction is at equilibrium or which direction the reaction has to go in order to reach equilibrium. So let's start with the situation where Q and K are equal. If you plug concentrations into Q and you get the same constant here as K, what that means is your reaction is already at equilibrium. Your Q and your K are exactly the same thing because the concentrations as you are plugging into your Q are equilibrium concentrations. So that makes Q exactly the same thing as K. Now now remember, in general, for a Q or a K, Q slash K, they're both calculated approximately as product concentrations on the top of the fraction and reactant concentrations on the bottom of the fraction. So a big Q or a big K indicates a situation where there are a lot of products and in that situation, whereas a small Q or K indicates less products and more reactants at that time. So let's say we calculate Q and we get a Q that is very small. What that means is that the bottom of this fraction must be big. So this is not, by the way, just to clarify, this is not Q divided by the K. What I mean is Q or K, since they're calculated in the same way. So a small Q here means that at this moment for this reaction, there are few products compared to reactions as there would be in K. So K is bigger, meaning at equilibrium there are more products and less reactants than there currently are in the reaction when we have calculated Q. And so that means the reaction will move forward from reactants to products. This is also called moving to the right. That's a very common terminology when the reaction is moving forwards to make products from the reactants. Now on the other end of the spectrum, if you calculate a Q and that Q is very large compared to K, What that means is compared to K, there are more products than there would be at equilibrium and less reactants. And so a large Q means that you have more products than you should have if you are at equilibrium. So the reaction is going to go in the backwards direction here, or we would say it will move towards the left, from products towards making reactants. And so the purpose of calculating Q here is to figure out, are we at equilibrium? Or is this reaction in a situation where it needs to make more products to be at equilibrium? So as more and more products are made, the Q will get bigger and bigger and bigger until it finally reaches K, and then the reaction will be at equilibrium. Or if we have a situation where we have tons of products to start, well, then there's too many products compared to K. The top of the fraction is too big, and so the reaction will move backwards, which will reduce the number of products and increase the number of reactants. And then Q will drop and drop and drop until it equals K, and then the reaction will be at equilibrium. Remember, the value of K remains constant at a particular temperature, but Q will change until the reaction is at equilibrium. So how might we use an equilibrium constant or a reaction quotient in comparing to the equilibrium constant? Well, if we're comparing, just to summarize here what we said in the last slide, if Q is less than K, that means that, again, there are too many reactants, not enough products. The reaction is going to go forward from left to right or to the right in order to make more products. If Q is greater than K, that means that at this moment there are too many products in the reaction, not enough reactants. So the reaction is going to move to the left. It's going to proceed towards the left, meaning products are going to get turned into reactants. And finally, if Q and K are the same, then we're at equilibrium and no net reaction is occurring. Now you could memorize these, but as usual, I don't suggest memorizing unless you absolutely have to. And this is certainly not a case where you have to. As long as you understand what we talked about on the previous slide, you should be able to reason this out in your mind. Again, as we move forward in this class, trying to memorize more and more things is going to make things really, really hard for you. It's better to understand them so that you can reason back to them in your mind, rather than trying to memorize every little thing on every slide. But this is how you use the Q and compare it to K. What about the various other ways in which we might use Q and K? Well, one way we might use Q and K is to determine what would be the K for a sum of multiple reactions. So we saw in the previous chapter that if we were forming reaction mechanisms to try to study the kinetics, we would have multiple reactions that we would make sure that they add together to this overall reaction. We can do that in trying to determine the K's of reactions. If we have the K's of a few reactions, but we can add up those reactions to get another reaction that we're interested in, but we don't know the K of. Well, to get the K for the overall reaction, you would simply multiply the K's of all the reactions that you added up. Why do you multiply them? I'll show you in a moment why that is with an example. But to get the K overall of a reaction that is added from multiple reactions, you multiply the K's of those reactions. What about if we manipulate the reaction? So we have various ways of manipulating reactions. We can reverse them. We can multiply all the coefficients by a whole number. If we reverse the reaction, what's going to happen is the Q or the K, they're going to get flipped. And so for the Q or the K for a reverse reaction will be 1 over the Q or the K for the forward reaction. And again, I'll show you an example of this in a moment. These are just a statement of these rules. But you'll see why these rules hold with the example that I show you in a moment. Finally, if the coefficients in a balanced equation are multiplied by a common whole number, then the Q for the reaction that you get from multiplying by that whole number is going to be the q to the power of that number. Or for k, if you want the k for the new reaction that was gotten by multiplying the previous reaction by a whole number, it would be k to the power of that number. Now let me use an example here to show you why this is. Let's start with this reaction here. Nitrogen reacts with hydrogen to make NH3, a very important reaction in the production of fertilizers, nitrogen fertilizers, which are based on ammonia. So here, if we wanted to write the equilibrium constant for this, we certainly could. I'll just write it on the side. It's products, so we'd put the concentration of NH3 here, so the K would be, and then we would square that since it's on the top. Then we divide by the concentration of nitrogen to the first power. Since there's a 1 here, it's not written, but there is. And also divided here by the concentration of hydrogen, and that would be to the third power. And so that's how we'd write that K, and that's written right here. Now, what if we now reversed this reaction? So now we reverse the reaction. So now the ammonia is on the reactant side, and the products here are the nitrogen and the hydrogen. Well, to get the K of this reaction, we would put the products here, which would be nitrogen, and then also hydrogen on the top, hydrogen concentration. We would cube that one because of the 3 here. And then we divide by the reactants, the ammonia squared. But what you'll notice is that this is actually, this equilibrium constant just flipped. What we've done here is we've flipped this upside down. If we take this and we flip it, whoop, whoop, right? If we take this and we flip it, whoop, whoop, we get this right here. And so the way to calculate the new K here is just to do 1 over the fraction. It's like if you have 1 over 2/3, that is equal to 3/2, right? You flip the, if you want to find the value of this whole fraction here, you multiply by the reciprocal of the bottom fraction here. So we flip it essentially. That's what doing 1 over something is. So 1 divided by K would be the K for the reaction that you got when you flipped or reversed the reaction. Another way to write this is you know, Kc to the -1 power. That means the same thing. Now finally, what if you multiply the reaction by a whole number? So I'm just going to point out the written K here. So here we're going to have the products on the top. So the product is the ammonia to the 4th power here, reactant on the bottom, nitrogen squared, and divided by the concentration of hydrogen to the 6th power. But what you'll notice here is that this is actually the same as, so this is Kc squared, meaning this is Kc here, and H3 squared over NH2, or sorry, N2 and this is to the 1st power here, H2 cubed, and then we square that whole thing. Well, if you square that whole thing, what it means is for the terms that are inside, you take the exponent and you multiply it by that. So this would be ammonia squared, ammonia to the 2 times 2 power, which is 4. Nitrogen to the 1 times 2 power, squared. Hydrogen to the 3 times 2 power, 6. And so if we multiply the reaction by 2 to get the new K, we would square it. If we multiply it by 3 to get the new K, we would cube it, and so forth. And so that's how you manipulate these equations in order to get the K's for equations that have been changed in some way. Now, what about if you add them, like we were talking about before? Well, that's what this next example is going to be about. If we add these two reactions on the bottom in a certain way, we can get this reaction here. So chemist wants to find the K for this reaction at 700 Kelvin, doesn't know the K. But the chemist does know the equilibrium constant for these two reactions at 700 K. Question is, can we use the equilibrium constants of these reactions manipulated in some way to find the equilibrium constant for this reaction? So in order to do that, we need to find a way in which we can add these two reactions together so that we can get this overall reaction. And the easy way to do that is just to inspect the reactants one by one and figure out where you can find them in the reaction here, and then replace them. And here I made a mistake. This should be 2HI. Okay. All right. So there we go. That fixes it. All right. And so now we're going to we look at this NH3 here and we say, well, which of our reactions has NH3? It's this first one. The NH3 is on the wrong side. So what we're going to have to do is we're going to have to reverse this equation. So we're going to reverse it, and so we're going to put the two NH3s on the left, and then we're going to have our double arrow, and then we're going to have the NH2 on the right, and then we're going to have the three H2s also on the right. And our K for this one, which I'll call K prime C1, is going to be 1 over 0.343. Okay. Now, also looking at this, we don't have to multiply this by any number, it looks like, because we have two NH3s here and two NH3s here. So we should be okay on this. Now let's look at the next reactant here, I2. So it's the second reaction that has I2, but it has 3 of them. So that tells us that we're probably going to have to multiply this second reaction times 3. We don't have to reverse it though, because the I2 is on the correct side. So is the HI here, and you can see the situation is the same for the HI. It's on the correct side, but it needs to be 3 times bigger. So it's looking like we're going to have to multiply this reaction times 3. So I'm just going to do that. So I'm going to have, well, I'll write it out first. H2 gas plus I2 gas makes HI. There's 2 of them, but we're going to multiply this all by 3. So we're going to multiply the H2 by 3, so we get 3. We're going to multiply the I2 by 3, so we get 3. We're going to multiply the HI by 3, so we actually have 6 now. And so our new K prime for C2 is going to be it's going to be 54 cubed. Okay. And now, if we want to get the overall reaction, we'd add these two reactions together. And I didn't leave myself too much space, unfortunately. But if we add these together, note that we're going to, we have 3 H2s on the right side here, and 3 H2s on the left, so those are going to cancel. And our overall reaction is going to be 2 NH3. Oh no, what happened? Okay. 2 NH3 from right here. We'll have 3 I2s, and then we'll have the 6 HIs and the 1 and 2. So we've got the overall reaction here. And the K is going to be, and I'll just write the K here. So the K overall, this one, is going to be the K prime C11 times K prime C2. And so it's going to be 54 cubed times 1 over 0.343. 54 cubed over 0.343. And so now we can calculate that. And so let's put that into our handy dandy calculator here. So we're going to have 54, and we're going to cube it. So we get this number, and then we're going to divide by 0.343. And we'll get about 4.6 times 10 to the 5th. 4.6 times 10 to the 5th. I'm going to do this to 2 sig figs. So we got 54 cubed. Does this keep happening? There we go. Okay, so 54 cubed divided by 0.343. Okay, and we get, so our result for this is now, I'll write it right up here. So our new K is 4.6 times 10 to the 5th. 4.6 times 10 to the 5th. Okay, great. And so now we've used all of these rules that we spoke of here. We had to reverse the reaction. When you reverse the reaction, it's 1 over the K for the new reaction. We multiplied this reaction by 3, so we had to cube the old K to get the new one. Then since we added these two reactions to get the overall reaction, we multiplied the K's to get the new K. And that K was about 4.6 times 10 to the 5th. Okay, you can see here on the slides I broke it down. I actually did each step in between and rounded, so I got slightly different, 4.7 times 10 to the 5th, but same thing. So that is how you manipulate K's and Q's. Finally, our last topic here is going to be about Kp. So Kc, the C in Kc stands for concentration. So the P in Kp stands for pressure. And so these K's can be, either of them can be used. So for gases, we can talk about the pressure or the concentration, either one. So for example, going back to our smog example here, N2O4 breaks down into 2 NO2s. If we're writing a Kp for this, well, let's say we're writing a Kc. So if we're writing a Kc, the Kc would be NO2 concentration squared product over the N2O4, right? A Kp is going to look just like that, but instead of concentration, there's going to be pressure. So here we'll put pressure of the NO2 squared instead of concentration, divided by the pressure of N2O4. Here P is referring to the partial pressure of each of these gases, so the pressure due to the NO2 here, the pressure due to the N2O4. For a general reaction, our same general reaction with reactants A and B with their coefficients small a, small b, and products C and D, their coefficients small c, small d, we get that the Kp is the pressure of product C here to its little c coefficient power times the pressure of product D to the little d its coefficient power, and then divide these by the pressure of the reactant A here to its power, divide by the pressure of B here to its power, its coefficient power. And so it works exactly the same way. It's just using pressures instead of concentrations. But the way you write it is the same way otherwise. Now there is a relationship between the Kp and the Kc. They are linked, and they're linked by the ideal gas law. So you may remember this R. Earlier in the class we used R with the different units. It had joule units, and it was 8.314 joules per mole Kelvin. This is the R with the units liters, atmospheres, moles, Kelvin. They're the same constant, just in different units. This one is 0.0821 or 0.08206 with one more sig fig. Liters times atmospheres, divide by mole, divide by Kelvin. Here the temperature must be in Kelvin for this to work. And delta N is the number of moles of gaseous products minus the number of moles of gaseous reactants. Now what I'm going to do is show you that in fact you can memorize this equation, but it's really important that you also understand where it comes from. It comes from applying the ideal gas law to the KCs. So you guys might recall the ideal gas law, PV equals nRT. Now, if we divide both sides here by V, and I'm going to show it like this for reasons that you'll see in a moment, we get, just on the left, the pressure is N over V times RT. Well, this, N over V, this is the concentration. So the pressure, so because it's the moles per liter, that's concentration. And so the pressure is really the concentration times RT. And so if we are calculating the, if we're going to calculate the Kp here, so the Kp equals, and let's use our general reaction here, little a, little b, in equilibrium here with little c product c, little d product d. So for our general reaction, just like we had on the last slide, for a Kp, it's going to be the pressure of C to its power C times the pressure of D to its power little d over the pressure of A to its power little a over the pressure of B to its power little b. So what we're going to do now is we're going to take, for each of these, we're going to take this definition here of pressure, all of this, and we're going to plug those right into each of these. And we're going to call this right here, we're going to call it the concentration of whatever. Okay. We plug that in now. So this is going to equal the concentration of C times RT to the little c power times the concentration of D times RT to the little d power over the concentration of A times RT, the little a power, times the concentration of B times RT to the little b power. And now I'm going to break this up. I'm going to factor out the RTs basically and leave the concentrations. So each of when you do an exponent to things that are multiplied, that exponent applies to everything that is multiplied. That's an algebra rule. We get concentration of C to the little c power, and then I'm going to put the concentration of D to the little d power over concentration A to the little a power, concentration B to the little b power. And then I'm going to put all the RTs here. I'm going to have RT to the little c power times RT, little d power, over RT, the little a power, over RT, the little b power. Well, all of this right here, well, this is just Kc. And then the rest right here, this is going to be, and so we have Kp all the way down here, Kp. So now I'm just going to write the last part in blue, Kp equals Kc, so that's all this right there, times RT. And the way that you do exponents, this would be, if like imagine RT is all like x. So you'll do, if you're multiplying exponents, you add them. So this would be C plus D. And then if you're dividing by exponents, you subtract them. So divided by a plus b. And this part right here, we're going to call this delta n. And so this is the change in the moles of gases. It's the product coefficients here added up together minus the reactant coefficients for the gases added together. And so, and this only applies to the gases. The solids obviously don't have a pressure, so they don't get included here. So this is the way you can translate between Kp and Kc. So let's look at an example of how we might do that. So ammonium hydrosulfide decomposes to ammonia and hydrogen sulfide gases. So that's right here. This is a solid decomposing to two gases. Find the Kc for the decomposition reaction, and we're given Kp here. Okay, so we know that Kp equals Kc times RT to the delta n. So what we're going to do here is divide both sides by RT, or equivalently, we could say we're multiplying times RT to the negative delta n power. So these would cancel. Multiply by RT, the negative delta n power. This means the same as dividing by RT to the delta n. So delta n minus delta n is 0. These go away. And so we get that Kc equals Kp to the RT delta n. So a couple of things we have to do. First, we have to figure out delta n. And so here we have a 1, here we have a 1, and here we have, this is not a gas, so it's a 0. So our delta n is going to be, for the products, 1 plus 1, and then minus, for the reactants, 0, no moles of gas. So our delta n is going to be positive 2. And then for temperature, it's 218 Celsius, but we can't use Celsius. We got to use Kelvin. So the temperature is going to equal 218 plus 273. And if we add those together, you can probably add those in your head, but we can use a calculator too. 491. So our temperature is 491. Now, because these are equilibrium constants, as I mentioned earlier, we can leave units off, but just be careful, because remember, your R has units of Kelvin, so your temperature better be in Kelvin, otherwise this is not going to work. And of course, your units for the other things, like here, we're going to end up with moles per liter, molarities for concentrations. Everything's going to work out. So since Ks don't have units, I'm okay with you leaving units off here. Notice that the Kp is not given with units, very common. So the Kp is going to be 0.19, and this is going to be, oops, I forgot my negative there. Negative. It's going to be times RT, so R is 0.0821. We'll use the one with 3 sig figs, that'll work fine. And then we're going to multiply that times the temperature, which is 491 Kelvin, and this is all going to be to the negative 2 power. Again, negative 2 because we divided by RT to the delta n, so that's the same as multiplying by RT to the negative delta n. This was to manipulate it so we can get Kc. So now we can plug this into our calculator. So we have 0.0821, I'm going to multiply this stuff first, times 491 equals, and then we're going to do to the negative 2 power, and then times 0.19. Okay, and make sure I punch that right. Yeah, I feel like there was something wrong there. Let me punch that again. 0.0821 0.0821 0.0821 times 491 equals, okay, there we go, that's more like it, to the -2 power times 0.19 equals, and we get about, to 2 sig figs, we'll have 2 sig figs since 0.19 has 2 sig figs, 1.2 times 10 to the -4 power. Okay, so 1.2 times 10 to the -4, that is Kc. And that is our answer. So that's how you interconvert between Kp and Kc. And here's the answer there, same answer. And so in the next lecture, we will cover heterogeneous equilibria. So you just saw an example of a heterogeneous equilibrium. You'll notice that essentially we ignored the solid because we said it wasn't a gas. And this is going to be generally true. So I'll talk more about that in the next lecture. I'll see you then.